In 1905, Albert Einstein published the theory of special relativity, revolutionizing our understanding of time and space. Before Einstein, it was believed that time was absolute, the same for all observers. However, Einstein showed that time is relative, flowing at different speeds for observers in relative motion. Imagine two people watching lightning strike a tree. If one of the people is moving towards the tree, they will see the lightning strike slightly before the other person. This is because the light from the lightning takes less time to reach the moving observer. Special relativity is based on two fundamental postulates. Media group, chalkboard with physics formulas, scientist writing formulas on chalkboard, man writing on chalkboard at stock at a distribute underscore equally. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is constant for everyone. These postulates imply that nothing can travel faster than light, and that time slows down for objects moving at high speeds. One of the most surprising consequences of special relativity is time dilation. This phenomenon means that time slows down for objects moving at high speeds relative to stationary observers. The closer an object gets to the speed of light, the slower time passes for that object. Imagine a clock that uses a light beam reflecting between two mirrors to measure time. If the clock is moving, the light beam travels a longer distance because it must also move with the clock. Since the speed of light is constant, the light beam in the moving clock takes longer to travel the greater distance between the mirrors. Time dilation has been experimentally verified using high-precision atomic clocks. In 1971, two atomic clocks were synchronized and one was loaded onto a jet plane. Upon its return, the onboard clock was slightly behind the clock that remained on the ground, confirming time dilation. The twin paradox is a thought experiment that illustrates time dilation in a vivid way. Imagine two identical twins, Mark and Paul. Mark stays on Earth, while Paul goes on a space voyage on a spaceship, traveling at a speed close to the speed of light. After several years of travel, Paul returns to Earth. According to the theory of special relativity, time will have passed more slowly for Paul than for Mark. This means that, upon his return, Paul will be younger than Mark. The twin paradox is not a true paradox, but a consequence of our limited intuition about non-inertial reference frames. The key to understanding the paradox lies in the fact that Mark and Paul are not symmetrical observers. While Mark remains in an inertial reference frame on Earth, Paul undergoes accelerations during his journey. Paul accelerates to reach a speed close to the speed of light, then decelerates to reverse course, and finally decelerates again to land on Earth. It is these accelerations that break the symmetry between Mark and Paul. Special relativity only applies to inertial reference frames, so we cannot use Paul's point of view to accurately describe his journey. Einstein's general relativity, which takes into account the effects of acceleration on the curvature of spacetime, tells us that acceleration has an effect similar to gravity, and that gravity influences the flow of time. Time dilation is not just a theoretical concept, but a real phenomenon verified experimentally. In addition to the experiment with atomic clocks on jets, time dilation is a factor in the operation of GPS systems. GPS satellites orbit Earth at high speeds and experience time dilation compared to clocks on the ground. If this effect were not taken into account, the position provided by GPS satellites would be inaccurate by several kilometers per day. Another example of time dilation is observed in the behavior of subatomic particles called muons. Muons created in the upper atmosphere travel at speeds close to the speed of light, and due to time dilation, their average lifespan increases from the perspective of an observer on the ground. This allows many muons to reach the Earth's surface before decaying, a fact that would not be possible without time dilation. Special relativity has significant implications for space travel, especially for interstellar travel. Because time slows down for objects moving at high speeds, a spaceship traveling at a significant fraction of the speed of light could reach distant stars in a relatively short time from the crew's perspective. For example, a round trip to Proxima Centauri would take more than 8 years from the perspective of an observer on Earth. However, for the crew of a spaceship traveling at 90% of the speed of light, the trip would last a little less than 4 years. Interstellar travel presents immense technological challenges, such as resistance to collisions with interstellar particles and cosmic radiation. To understand special relativity, it's helpful to think of time as a dimension similar to the three spatial dimensions. In this model, our universe is a four-dimensional space-time continuum. Imagine a sheet of paper representing two spatial dimensions. An object moving on this sheet of paper traces a straight line. If we fold the sheet of paper, the straight line becomes a curve. Similarly, gravity curves space-time. Time dilation can be seen as a consequence of this curvature of space-time. Despite the progress made in understanding time thanks to special relativity, many questions remain unanswered. For example, we still don't know if it's possible to travel back in time or if parallel universes with different time streams exist. Scientists are working on theories that could unify general relativity with quantum mechanics. It is hoped that these theories of quantum gravity can provide new insights into the nature of time and the possibility of time travel. Research on time travel is still in its early stages, but current theories suggest that it might be possible under certain extreme circumstances, such as the presence of wormholes. Einstein's special relativity revolutionized our understanding of time, showing that it is not absolute, but relative to who measures it. Time dilation has profound implications for space travel and our understanding of the universe. Although the twin paradox seems to defy logic, it is actually a consequence of our limited intuition about non-inertial reference frames. Einstein's general relativity resolves the paradox, showing that acceleration influences the flow of time. The search for a unified theory of physics could lead to new insights into the nature of time and the possibility of time travel. Our understanding of time is constantly evolving, and every new discovery brings us closer to a more complete understanding of the universe and its wonders.